what we've been talking about on Friday and we'll continue talking about today is the difference between treating sort of complicated deformable objects as points and considering the full complexity of the ways that they can move and where energy can go into their motions. And so remember that we've defined, we're using this word translation, which in its technical mathematical sense doesn't have anything to do with going from one language to another. It means moving from one location to another. So the translational kinetic energy is the kinetic energy associated with the entire object just moving from one location to another, essentially the motion of the center of mass. And remember that we've been distinguishing between the motion of the center of mass of a complicated system and the motion relative to the center of mass, which can be rotation or vibration, things like that. So just to get all of our definitions and results down in one place, remember that a long time ago we defined the total momentum of a system as just the sum of the momenta of all its individual pieces, which could be atoms or tennis balls or something like that. The new thing we did was to define the location of the center of mass of an object as a weighted average of the positions of all of the massive objects making up the system. So it's M1, R1, M2 plus M2, R2. Okay, so you should have this in your notes, and it's also in the book. And we get the velocity of the center of mass of the system just by differentiating this. Okay, so the velocity of the center of mass of a system, and remember the center of mass it's pretty much what you think it is, so probably there somewhere. All we do is since velocity is rate of change of position with time, all we have to do is differentiate that, and what we end up with is M1 V1 plus M2 V2 plus over the total momentum. But that's actually, but the total mass, but this is the total momentum, so that actually ends up being in the non-relativistic approximation. So this is, everything here is V less than C. So we get, this is 1 over M times P total, and so of course P total is equal to M total, the center of mass. And we also divided the total kinetic energy of an object, which is maybe stretching and vibrating and rotating and flopping around, into the translational kinetic energy, that is the kinetic energy associated with just moving from one location to another, plus the kinetic energy relative to the center of mass. So that means the center of mass is moving, but this thing may also be spinning or vibrating or stuff like this. So we can actually write this as, let's see, this is equal to K translation plus K rotation plus K vibration. And we have the translational kinetic energy is just the half M total, the speed now of the center of mass squared, or if you like, the magnitude of the total momentum squared over 2 times the total mass. So these are, some of these are results, some of them are just definitions. And we spent all Friday just kind of getting used to this taxonomy and identifying rotational energy and vibrational energy and translational kinetic energy. And now we're actually ready to do some physics with it. And we can apply the momentum principle and the energy principle. And the point of this whole chapter and this whole discussion is that we can either treat these big floppy systems as if they were points, or we can actually look at their full complexity, the fact that they stretch and vibrate and rotate, and we can apply the momentum principle and the energy principle. When we do this, we will get different information. None of it's wrong, but the information's different. And so by analyzing the system as if it was a point and then analyzing the system in its real complexity, we can actually compare things and get some information in particular about these internal things, the relative things, the rotation and the vibration. So that's the thing we're going to do. So just to start off and show why this is interesting to do, let's remember that the momentum principle for a multi-particle system, the rate of change of the total momentum with time is the net external force applied, or in the discrete finite time version, the change in the total momentum of a system is the net force applied to it by objects in the surroundings times through the time interval. This is the net impulse. So I want to ask you to think about the following system and see what you think is going to happen. So we have these two puck thingies lying on the ice, on a slippery surface, and we're going to apply the same force to both of them for the same time. Okay? But they're not points, and where we apply the force could make a difference. So puck number one has a string wound around the edge. Okay? So when we pull the string, two things can happen. It can move, and the string can unwind. Whereas puck number two just has a string attached to a nail in the middle. Okay? We're going to apply the same force, F, for the same time, 3 seconds. And I want you to think about what you think is going to happen. After 3 seconds, what's going to happen? Number one's going to move farther than two. Number one is the one with the string wound around it. Number two is going to move farther than one, or 1 and 2 will move the same distance in that 3 seconds. All right, so let's see what you predicted. Okay, the most popular prediction is that 2 will move farther than 1, and that's what most people say. And can someone say why you think 2 will move farther than 1? Seems sort of, yes. 1 is going to spin. 1 is definitely going to spin. Okay. If you thought 1 would move farther than 2, what's your reasoning? You must have thought something. Okay, what if you thought they'd move the same distance? What was your reasoning there? Say, they have the same mass. Okay. So, some people thought it would be the same. Can you articulate? Okay, well, let's think about it. So everybody, this is one of these questions where you actually just have to get this intuitive guess out of your system before you can think about physics principles. So we did this, and most people guessed that puck 2 is going to move farther. Now let's actually try to apply the momentum principle and just see what it predicts. Okay? Just see what it says. So for puck 1, okay, P final is going to be P initial plus F net delta T. P initial was 0. So it looks like the final momentum of puck 1 is going to be determined by the net impulse applied, which is this force times the time it was applied. Puck 2. And that means that V final is going to be P final over M, so F delta delta t over m, right? Buck 2, P final is P initial plus F net delta t. P initial was 0. According to the momentum principle, it ought to have the same final momentum, right? So V final for Puck 2 is going to be P final over m, which is going to be F delta t over m, and it looks like they should have the same final velocity. Yes?
The final velocity for 1 is an exterior point, while the final velocity for 2 is the point, the center of the mass.
No, we're talking about the velocity of the center of mass. We're talking about the total momentum, which is m total v center of mass. So if they have the same total momentum, they've got the same v center of mass, they're traveling with the same velocity. There's no way around this prediction. If the momentum principle is really a universal principle, if it truly applies in this situation and there aren't any qualifications of except if it's rotating or except if it's vibrating, then there really isn't any way around this prediction. Right? Doesn't seem possible, does it? Seems like there's got to be something wrong. But yes.
In number 1, the force isn't acting directly on the center of mass.
Well, but nothing. This doesn't say anything about the force acting on the center of mass. You're right. You're right that the location of where the force is applied is going to affect the motion. But the momentum principle, which says dp total dt, delta p total is F net delta t, that predicts. We're not doing any fancy math here, right? This is pretty simple. That predicts same final velocity and therefore same displacement. So what we're predicting using the momentum principle really doesn't sound at all like what we think is really going to happen. So here's a simulation of ePython simulation, what the momentum principle predicts. Whoops, there we go. So here's our two pucks. The top one's pulled from the edge, the bottom one's pulled from the center. And all we've done in this VPython program is just apply the momentum principle and the angular momentum principle. But anyway, this is what it predicts, that they're going to actually be traveling with the same momentum, therefore the same velocity, therefore their displacements should be the same, but you're absolutely right that the top one should be spinning because there's a twist applied at torque, right? That's chapter 10, angular momentum. But notice that, let's do it again, okay, because this is the prediction. Notice that the momentum principle predicts that when the same force is applied for the same time, we get the same total momentum, so motion of center of mass ought to be the same. But it doesn't say anything about the distance through which the force acted. Okay, the force absolutely acted for the same time, so same impulse, same momentum. What it doesn't tell us, though, is that if you're pulling on this thing, your hand moved farther. So that's not an energy thing, is it? What is force times distance? That's work. So the same impulse was applied, but the same work was not done. Some land just says they have to move together, but energy land says some other things can be happening. Or it could go into spinning energy. Okay, so let's see what actually happens. We have here a video of the real thing. This is Dr. Sherwood.
Here we have equipment that's sort of like two pucks sliding on ice. What we really have are two heavy pulleys riding on two carts that will roll on these long aluminum tracks. One of them we're going to pull from the center. One of them we're going to pull from the edge wrapped around it. I've got them locked here for the moment so they don't move. You'll see that there are little yellow tags on here so that you can see how far the piece of string moves, in particular as it plays off this pulley as it moves. So these guys are going to move down here. What's moving them is the strings come down to pulleys, come up over these pulleys, come over those pulleys and down to what's called an idler pulley, from which we'll hang a weight, which will then pull down. And this arrangement assures that the force in that string and the force in that string are exactly the same. So we've contrived a situation where we're applying the same force to both of these pucks, one pulled from the center, one pulled from the edge. And so we'll want to then see what happens to the motion of the pucks and also to how the little tags on the strings move. What I'm going to do is I'm going to release both of these carts, and the strings are going to pull, and what's going to pull them, as we said, is that hanging weight down there at the end. So here I go. I'm going to let go now, and you see the weight starting to fall, pulling on both of the carts. Here we have the two pucks. One can rotate, one can't. This one here is pulled from the center. This one is pulled from the edge with the string wrapped around it. We also have little plastic flags attached to the strings, so you can see how those move. And for the rotating one, some string is going to pay off this being wound around the edge, so that could move in a different way. Watch how the flags move, and watch how the centers of the two pucks move. We're going to apply the same force to both and a release, and here we go. And you see that the pucks are moving together. The centers are moving together. Now, eventually, the weight hits the floor at the other end. But for this long motion here, the centers moved together. The flags did not, because they were pulling more string off the rotating puck, and that extra work went into making it rotate. Okay.
So that's pretty interesting, huh? So in the real world, looks like the momentum principle was right. It actually predicted what really happened in this situation, but it didn't give us all the information we might want. Okay, it really did tell us what was going to happen to the motion of the centers of mass of these two pucks. It said they will move together, and they did. So momentum principle wins, one for the momentum principle. But what it didn't give us any information about is how much rotation there was in that second puck. Okay, so it's correct, but it's not complete. So we need the energy principle, the easiest way to analyze this. We can come back and look at this when we get to angular momentum and see what the angular momentum principle is going to tell us about this too. But what we're going to do now is look at what the energy principle tells us about this situation.